We had a few more questions when talking to Sean last week, and in classic engineering fashion, when he said he'd done a lot of wave protection design, and Zach and I have no idea what that means, we needed to hear about it. So join us at the wave pool, where Zach and I don't really even know the right words for the questions. What is the goal? Where are the waves? How hard do they push you? I don't know, but luckily Sean does, and he's willing to tell us about it. So let's see how much we don't even know about this subject and learn a little bit about wave loading.
The Structural Engineering Podcast.
Sean, welcome to the Structural Engineering Podcast, or welcome back. Would you mind introducing yourself again?
How's it going? My name is Sean Buckner. I am a structural engineer based in Southampton, New York, on the east end of Long Island.
Today, Sean, we're going to talk about wave loading, which I think Zach and I know very little about. So feel free to correct any of our questions, even if that's just not how this works. Because I don't know. For people that normally design in dry conditions, myself included, what does flood design actually become? When does it become a structural concern? Like when does the building need to incorporate loads from floods, waves?
For sure. So in terms of actually accounting for flood loading or wave forces, FEMA does do a very good job. They have a interactive online tool. There's a website, but I think if you Google FEMA Flood Map Service Center, you can actually search by address, and it's an interactive map that shows flood zones, different lines, including the LIMWA, which we'll dig into, the limit of moderate wave action. And it designates the beachfront properties or some of the inland properties, depending on waterways and whatnot, as AE, VE, or X zones, which we'll dive into each of those, I think, more specifically.
So is flood engineering something that comes up once in a while, or is it a constant factor in the projects you're working on?
I would say that probably 20 to 30% of the projects that I work on the East End are, either beachfront or adjacent to some kind of inland, a lake or something like that. We do have on the south shore of Long Island, we have a barrier island that houses a lot of, Dune Road and Meadow Lane, some of the higher end roads. So you kind of get two waterfronts, both the ones on the barrier island, but then as you come inland and you have Mecox Bay, Shinnecock Bay, that kind of brings the, some of the flood zones in further. And we have a lot of lakes as well that have some flood considerations. So yeah, I'd say kind of in the 20 to 30% is where you actually have to design for one of the VE or AE zones.
So I've done a couple beachfront buildings, but in these, it's always been some distance above the high water mark as our baseline, and we didn't have to consider. I hope. I don't think. I wasn't told to. How do you decide when a structure needs to resist flood or wave loading? Like what triggers the shift in the design approach?
Yeah, so that comes down to that on that FEMA map, they designate zones as I alluded to, the AE and the VE. So essentially there's three main zones: AE, VE, and then coastal A. On the map, you'll see zones such as, you just alluded to elevations and, that precluding you from having to design. There will be like an AE8, a VE10, and those, refer to NAVD 1988 elevations and essentially tell you the base flood elevation of that property. And then the AE or the VE determines either you have to just consider in an AE zone, you have to consider just basically a uniformly rising groundwater, essentially like a flood. In a VE zone or a coastal A zone, you actually have to consider the basically rushing waves. And the difference in the AE, the coastal AE zone, is it's an AE zone, but it's seaward of what's known as the LIMWA line, the limit of moderate wave action. So essentially I group it as AE, and then VE and coastal A are one group. And I think the only reason they designate that differently is because FEMA is involved with insurance. And I think it just is an insurance thing rather than a structural thing.
Can you give me a quick scale of if you have standing water pressure versus wave loading? Is wave loading 10 times as bad, or are they, twice as any scale if I can think about this right?
Yeah, so I would say the devil's in the detail with FEMA, where they actually, a lot of the requirements counteract the expected kind of loading that I think you're expecting to be on some of these structures. So by that I mean in an AE zone, you're allowed to have an enclosed basement. It cannot be livable space, finished area, or anything like that. But you can have an enclosed with solid concrete walls and a concrete slab on the bottom. It can only be I believe 4 or 5 feet max. They have a nice diagram in one of their technical bulletins, but essentially what you do is you place flood vents around the perimeter of uh, the structure. They have a ratio of you need to provide 1 square inch of flood venting for 1 square foot of enclosed basement, which I guess according to their calculations, under a flooding event, allows enough water to come into the basement so that you don't have a imbalance in hydrostatic pressure inside and outside. So they're basically assuming you have this bathtub and you're going to put a couple holes on the outside to allow water into the bathtub so that it doesn't become a retaining structure, retaining both the soil and the water on the outside. So that's the AE zone. You kind of get rid of the hydrostatic in a way. Then on the other hand, there's VE zones. That's the zone that you have to account for rushing water and breaking waves. FEMA does require you to meet certain requirements that really lessen the amount of load that's going to be imposed on your structure through some of their technical bulletins. If some of your listeners want to check them out, there's FEMA Technical Bulletin 5, which is called Free of Obstruction Construction. And there's Technical Bulletin 9, which is Design and Construction of Breakaway Walls. So you need to comply with that, along with, they basically base that off of ASCE 24, which has a bunch of, loading and requirements for flood zones and whatnot. But in those technical bulletins, as the, wording says, free of obstruction construction, is you can have an enclosed basement area, but it needs to consist essentially of intermediate piers, concrete piers that hold your house up. And then in between that, you need to have breakaway walls. That can either be essentially lightly fastened, nailed wood walls or unreinforced CMU walls. So in the event of a flood, those can break away, as the name suggests, and you're allowing the free of obstruction flow of the rushing water. So then you kind of come down to you're only designing for some rushing water that's hitting your piers, whether that be, 18-inch by 18-inch piers or something along those lines, which is still something you need to consider and design for, but is way less than an entire wave breaking on, the side of a solid concrete foundation wall.
So even going back a little bit, thinking coastal regions and houses, and they have seawalls or some sort of infrastructure, especially if they're right there on the water. What are the elements that are being designed for floods or wave impacts? What are you personally involved with where you're utilizing these, and what elements are you designing?
Yeah, so like you said, the house is one kind of animal in and of itself. A lot of times we'll just design a house that is going to meet some of those requirements I just outlined. The shorefront protection is really something that is triggered, I would say, almost a majority of the time. It's on existing houses that have seen tremendous erosion over the last 20 to 30 years. Someone, comes out here every summer, continues to watch their beach erode away, and then they start to actually, literally fear that they're going to start to lose their backyard and their house, at some point. Some of the aerial imagery I've done while, studying specifically stone revetments, the erosion rates over the last 20 to 30 years, I've seen people lose 60 feet of property, and they're trying to protect their asset. So a lot of the times we come in and we do those on existing houses. Something to mention is, because of zoning setbacks, rear yard setbacks to primary houses, and then also, buffer zones from wetlands or waterways, which are kind of governed by either the DEC or town conservation boards. Typically, it's not like you have a house that's, close to right on the water, and then you have to do a bulkhead that's going to retain the entire house and protect it from the water. So typically there's a decent amount of space, and whether that's a bulkhead, a sheet pile bulkhead, or a stone revetment, which is a little bit more acceptable, and I think something we need to dive into is the environmental considerations. But those are typically kind of protecting land more than they're supporting your primary house, because there's still a decent amount of buffer between the two of them.
Okay. Yeah. No, that helps make sense. Can you help us understand a little bit better the difference between, just being near the water and then truly being in this wave impact zone? Is it just the kind of, as you mentioned already, those FEMA designations, or is there more to that? Wave loading, flood loading, kind of really setting the stage there.
And where does the FEMA designation pull from? Is that in elevation? What data are they relying on?
Yeah. So to your point, Zach, mainly it is, kind of looking at those FEMA maps and seeing what zone you fall in, if you're seaward of the Limwa or not, so on and so forth. And, a lot of the times architects, they're kind of the first member on the team with the client. They start to study these things. They start to plan the first floor elevation around the base flood and the design flood elevation. And the surveyor is going to plot the exact designation, what zone it's in, things like that. So there's already a couple team members probably, morphing the project into what it needs to be before, I may get on and, advise exactly on the fine-tuned structural details that are needed. Max, it's proximity, but it certainly is very much elevation. There's certain stretches of the Peconic Bay that are very steep dunes. So you could have a house that's waterfront and you could probably throw a football into the water, but it's going to be a football into the water 40 feet down. So when you're when you're that close, but you're that high, flooding is no longer an issue. It's going to be on the dune and whatnot, and groundwater is not an issue. It's really when you're very close and basically at sea level. A lot of the East Hampton area has some kind of towns that are basically like on the beach, and you might drive down it after a rainstorm and there's sitting groundwater. So they're really, it's like a Long Beach type situation and whatnot. So yeah, that's the FEMA standpoint. I think something I just mentioned with the groundwater is also something that's similar to what we're talking about today, but it is still water involved and whatnot. So I think it's important to mention, even on properties inland around some of these lakes we talk about, we do sometimes see, you might not be on the water, but groundwater might be 4 feet down, or 3 feet down or something like that. And I think a quick aside, because I think we want to focus mostly on the FEMA stuff today, but in some of those areas, sometimes, we need 36 inches from grade to the bottom of footings to protect from frost. So if groundwater is 2 feet down, sometimes we're forced to even just go with, pile solutions to, not be in violation of the frost protection and things like that. And then furthermore, with some of the wealth that's on the east end of Long Island, we have some clients who, we tell them groundwater is 5 feet down. Sorry, you can't have a basement. We can do 4 or 5 foot frost walls basically around the house and do a crawl space, and you can have your first floor and second floor. And they're really decided they want a basement, and I understand, because it's 150% basically more house. We do get involved with houses that basically you dewater, you do the foundation. We design it as a hydrostatic foundation with very thick foundation walls, a thick mat slab, and then we design it to resist all those hydrostatic pressures, both the buoyant on the slab and then inward on the sides of our walls. And essentially, when you're in the basement, you're underwater. You're in a bathtub, submarine type thing. Sometimes with that, if it's a very, if groundwater is very shallow and we want to go with a 10-foot, 9-foot basement, sometimes we even need to do helical piles in tension, acting as like fingers holding down, against the buoyant forces.
Are you also pumping out, or is this you're a bathtub in the water? Like, is there a belt and suspenders style approach that we also pump out the groundwater?
They'll do some pumps in the basement, especially if there's window wells and stairwells and things like that water will come down. But really what we do, and it ties into now the FEMA kind of. FEMA typically, they, like I said, the AE8 or the VE10, things like that, that's the base flood. And then what they typically do is require a 2-foot freeboard. So if you're in an AE8, you actually need your first floor to be at elevation 10. So they're kind of expecting a 2-foot surge above their, worst case water for, future storm surges, rising groundwater, things like that. So that's kind of a similar approach that we do is we find highest groundwater. We say during the construction we're going to dewater, but then when we design for the buoyant forces and hydrostatic pressures and everything, we actually add 2 feet to the highest expected groundwater. And really it's kind of just now a concrete vault, and
Yeah.
they just have a couple pumps inside.
Wow. All right. So when we were looking into this, the little bit that we have here is there were a few words that I did not know the definition of at all. So I'm going to throw them at you right here. Still water elevation, I have a guess. Run up and overtopping. How do these translate to structural loads, essentially?
Yeah, so still water elevation, in in layman terms, is basically the level at which groundwater is going to rise during a storm. So it's kind of that flooding elevation type thing. It's kind of the raise in sea level. Uh,
Is that related to the 2 foot above groundwater? Or is that the buffer that you have on top of this
that's
storm still water line?
That's more, I would say the still water is more closely associated to the base flood elevation, which is going to be your AE8. And then they put on that 2-foot freeboard on top in excess of that for kind of, unprobable or unpredictable events. And something, so, so FEMA defines the AE and the VE zones really for houses. The still water, wave run up, and uh, overtopping are actually, and I don't mean to create this division between house and coastal structure, but it actually is a little bit of two different trains of design. So those terms are a little bit more for those bulkheads, revetments, things like that. So it's a good question. I mean, Stillwater and AE8, their projected base flood elevation really should be very similar. FEMA provides those maps that give you those zones, but they also, what I use when I design coastal structures is they have flood insurance studies. And, I don't know how granular they get everywhere, but they have a study for Suffolk County, New York, where it's basically a map of the entire Long Island, and they have transects that connect, in some of the bays, in the oceans, in the Long Island Sound. And you can look up, okay, on the map, I'm transect 43. Then you can go to the table and you can get the 10-year, 25-year, 50-year still water elevations. I should look into how that compares with some of these flood zones, but those do vary a little bit more than your standard AE 10, 8, 9. So that's kind of with the still water. The wave run up, again, and it's kind of easy to think about this more in terms of like a coastal structure that's on the beach. So essentially the run up is when you have a breaking wave and that wave crashes and starts to flow up the beach. The run up is essentially the vertical elevation that reaches as it's not the peak of the wave itself. It's the highest elevation that the water, propagates up the beach. So that's run up. And then overtopping is, now you think of, this is part of, the calculations, and it's kind of the chicken and egg. Once you design bulkheads, you typically don't allow any overtopping. You design a bulkhead to be really a hard structure that retains soil and the waves break at the face of it. But with some of the revetments and things like that we design, it's actually okay to allow some of the water to go over the top of the crest. Especially, why it becomes very pertinent is the environmental considerations. Like I said, the DEC and the, conservation boards of East Hampton, Southampton, everyone, they don't want everyone just putting a bunch of boulders in front of their house, or just everyone building, bulkheads everywhere. And actually, background on that, bulkheads are kind of an old school thing. All marinas have them, this, that, they protect, from water. But as erosion started to continue, a lot of houses on the East End have bulkheads protecting their property. But the town, the DEC, the conservation board started to realize, we're just going to end up making an entire wall around Long Island, and that's not going to be good for, the environment, the animals that are living there, all that stuff. So the revetments kind of became like a quote unquote softer solution. So you can kind of think of it as like a bulkhead is a wall, a wave hits it, crashes, gets directed, all the energy gets directed down because it has nowhere to go when it hits a sheet pile wall, gets directed down and starts to scour out the foot of the bulkhead. With a revetment, it's a gradation of different stone sizes and everything like that. A lot of big boulders to hold it in place, but a lot of smaller boulders filling it in, stones, cobble base, things like that. But the advantage with that and why it's more advantageous for environmentalists is a ton of the wave energy is going in and getting basically sucked into the void spaces between the rocks. Some of it is getting redirected when it hits the face of the rocks, but it's way less impactful to the surrounding beach areas. So that kind of became a solution that had become more prevalent and more acceptable. But now tying back to the overtopping thing, in certain areas, when you're just on a lake, one of these lakes, or if you're inside the barrier island and your fetches, which is a big part of predicting waves during storm events, is the distance to, like, the uninterrupted distance across the water to another body of land. So essentially, like, how much momentum can a wave build up? So if you're on the ocean, it's tremendous. So in some of these higher wave force areas with taller waves and things like that, some engineers were coming up with, you need a 7-foot stone revetment or something along those lines. The town didn't like that either. Just because it was a revetment, they didn't want people building, mountains in front of their houses. So DEC kind of has a general rule, and sometimes there's push and pull on it, but they kind of like to cap you at a 4-foot revetment, regardless of what, not the engineering says, but typically they say, okay, you're saying you want a 6-foot revetment. Tell us what a 4-foot revetment's going to be, and maybe that's only 12, quote unquote, 12 years of protection in a 12-year storm rather than the optimal 25. And they say, well, do the 4 for now and let's see what happens in 12 years, because they don't want to give you, all of it at once, which I understand. So in that sense, then we kind of have to go to a 4-foot, and then we have to evaluate the overtopping is essentially a flow rate of how much water is going to get over the top of our revetment, and that, which is okay, and it's going to, hit the ground behind it. There's going to be less scour because you have all these rocks holding that ground in place, but it's just another part of the kind of revetment design.
Well, with someone, and especially myself, and as Max said, never doing this before, like load wise, I know it's probably all over the place, but what are we talking? Is there impact loading that comes down to this? I'm thinking, a big log is coming out of the ocean or something and flies up. Are we talking 300 or 3,000 PSF worth of loads? Like, give us some ranges here.
So with the revetment things and like that, I can't give you an exact, and I wish I knew like a PSF, and that would be, a good metric to know. But basically what we do is we use a lot of empirical formulas and whatnot to project wave heights and things like that during certain reoccurrence storms. And then it's a pretty old school software. The user display is definitely dated, but it's called ASCE, and I wish I knew what that acronym was, but it's ASCE and CDOS. Are two softwares. Basically, you get a flash drive from these people. This guy was a hydrologist, and you plug in your wave height, your fetch data, all that, and then there's a ton of different modules in it that will give you, like for the stone revetment, will give you stone gradation, necessary height, crest height, toe height, things like that. So it's a little bit less of like our typical structural engineering, formulas where it's get a uniform load, design, rocks to resist that. I wish I knew the inner workings of that software, but it's some of that legwork and the background in the breakwaters, the flood insurance studies for the still water heights and things like that to gather all that information, plug it in there, and then it kind of gives you an output.
Okay.
I like that they
So
mail you something. It feels a little close to the AOL mail you CD days.
Yes, yes, exactly.
So let's move into talking about that. I'm talking about a house. So let's say a house is elevated up on piers or piles. Can you walk us through kind of what does the wave loading do to the elements differently from the walls to the slab to you kind of already mentioned a little bit about that, but could you go into some more details about the loading on the piers?
Yeah, absolutely. Like mentioned, the walls need to be breakaway. Similarly, any slabs also need to be unreinforced slabs so that they can be breakaway in a VE zone. In an AE zone, it can be a solid slab because we're doing those flood vents. In terms of going back to the breakaway walls themselves, uh, something that I reference a lot, and the most common is a wood breakaway wall because it's the cheapest. There's no reason to really infill with CMU if you don't need it. And in that design bulletin number 9, they provide tables for the height of your basement, the spacing of your piers, and then they give you, the certain nailing patterns that you need to have it break away in that storm. So that's a useful tool in terms of designing your breakaways. If you put unreinforced CMU, it's unreinforced CMU. It then you kind of assume all that stuff, breaks away and whatnot. That's where I've mentioned ASCE 24 and the FEMA technical bulletins, but there's not an elaborate flood loading chapter in ASCE 7, but the part that it does have is all the equations for your breaking wave loads on a pier, breaking wave loads on walls and things like that. If you're in a situation that needs that, and they have it for squares, circles, that's the piers and whatnot. They have it for walls, but that's where we refer back to, and then you have to determine your, breaking wave force on your piers. There's also provisions in ASCE 24 for determining scour. So when you have both your piers, but then you also have grade beams and piles, there's certain formulas which are typically in the range of like 2 to 4 feet of scour that you need to account for, which is specifically very relevant when we're doing helical piles. Helical piles, the most basic one that we use is almost a 3-inch, basically 2 7/8 inch round diameter shaft for the helic. So when you start to scour 3 feet below the grade beam, and we need to anticipate, the lateral forces still being applied to that during a storm. There's going to be wind forces and everything like that. It's easy to compromise those. So a lot of times when we do helical piles, we need to also, depending on how low we can go. If we can go low and kind of be below that scour depth, then we're pretty confident with standard helical piles. If it's a matter where groundwater is 2 to 3 feet below grade and we're doing grade beams essentially at grade rather than buried, we need to do battered piles. So, maybe at like a 45-degree angle around the sides. And then those really help even when things scour. If you start to get some horizontal loads, it's not going to be so much bending in vertical helical piles. It's more going to end up being tension and compression in these battered piles.
Yeah. What is the depth you're looking at for battered piles in this case?
Most piles, I would say, are kind of, given the loading that we need, and then, to achieve the tension and compression in the horizontal direction, I'd say we're kind of in the 25 to maybe 40-foot range with some of these helical piles. The 40s with some of the higher compression needs, maybe, some of the pools that we need to do, when you're in an area that doesn't have great soil bearing capacity and you need piles, then we need to design the pool to be on a system of grade beams and piles, which is a tremendous amount of concrete and water. So those require some higher torques.
Is bedrock often an issue on the coast? The little coastal work I've done is, bedrock was always a foot down. So we were doing anchoring system to this, but thinking helicals, of course, can't get there. Is this something that you're seeing a lot, or was unique to the north?
Yeah, on Long Island, nothing. No bedrock in
Yeah.
sight. I've had some jobs where it's really loose sand, and they've torqued down helicals 70 feet. And
Whoa.
that and
Okay.
normally they'll do one or two of those, and they'll call me and they'll be like, "What else can we do here?" And then we'll start to increase the helix configuration and things like that to limit the depth that they need to go to achieve the torque. But nowhere in sight. I've done a couple projects upstate and one in Connecticut recently that
Mm,
bedrock was way more in play. So that's a
yeah.
different challenge. But yeah, we're on a big beach essentially.
Do you so because I'm so unfamiliar with all these other codes, I'm gonna ask a ASC 7 style question. Do you lean on the standard load combinations that we work on here, or are flood conditions handled differently than the typical ASC 7 ones that we're very used to?
Nope. So we use the standard ASC 7. They have hydrostatic loading factors in there, and really the only line that ASC 24 has on load combination of loads is go see ASC 7. So that's our main resource for that.
Yeah, so when you're looking at this, though, like how useful are the FEMA maps or firm panels when you're actually trying to engineer the site? Does that basically give you all the information you need?
Yeah, essentially. I mean, it's that gives us the basis of the systems that we need, again, the flood vents or the breakaway walls, but then the complexity of the house, we have those piers. If if the architect is electing to go higher, obviously our pier heights are going to increase, and then you're going to have some more moment from breaking waves on that and things like that. So, it gets more nuance with the exact design, but uh, the baseline, what system do we need to use, uh, is determined by that. And another important thing to note is in an AE zone, it's if you have the bearing capacity, you can go with shallow foundations. In a VE zone, because of the scour that we were just talking about and whatnot from the breaking waves, you shallow foundations are not allowed. So even
Okay.
if you have the bearing capacity, you got to go deep because they're worried about undermining the footings and whatnot.
Wow.
And are they worried about life safety or the economics of keeping the house when you're thinking about this, like from a flood perspective?
I would say life. I mean, so with the free of obstruction construction in that design, that technical bulletin 9, they have a lot of cool pictures from old, beachfront houses, maybe on the Jersey Shore or something like that. But you could see the amount of damage that's done to the outside of the house. And I think this is also an important note to make, and something I thought about when I started really diving into flood design and whatnot is, you know, if the client's willing to pay, why can't we just, do an encased basement that we heavily reinforce like we do with the hydrostatic basements and things like that, and resist the forces of the breaking waves. But something they allude to in there is that's great. Your house is, protected, your structure is protected that you designed, but now you're redirecting wave forces at your neighbors and things like that. So, if you build a mega mansion next to this old bungalow that's been there 100 years, now, I think it truly comes into life safety where you could build this huge concrete structure, and now the bungalow, let's see how it fares in, a 100-year storm by itself. But are you forcing even more pressure at them, that can wash away the house and, become a life safety issue for neighboring properties that weren't designed for the loads themselves, nor the
Yeah.
increased loads by you redirecting them.
Are with not being from that region, I'm curious, like, when a flood's going to come and everyone's aware of it, a hurricane or what may hit that far up, are people staying there at their houses and say, "Hey, I've got my walls will break away, so we're good. We'll just stay here through the flood," or most people leaving the area? I'm just curious.
Um, I don't think we've had any storms of this, nature that
Okay.
really, like, I doubt that any real breakaway walls have been broken away. I think, that's why I allude to, maybe some of the houses and the case studies they did were a little bit more southern. Um, but I can't really remember. We've had even in I mean, in Sandy, Hurricane Sandy, which was I think 2012 or something like that. That was probably the most severe storm we had, and I think that triggered a lot of this because, and again, I'm from Nassau County, so up island, and I can speak. Long Beach is, very much like I said, is a community built at sea level, right on the water, but a ton of those houses were just houses built on the ground, and there was significant like crazy damage to almost every single house in Long Beach. But now almost every house is built up on stilts, on the
Okay.
piers and the breakaway walls with the either like a lattice so that you can, have some kind of, privacy and whatnot. So to answer your question, I don't think everyone really left during Sandy, so people do stay. Uh, but I also don't think that a very small minority of structures were actually designed to FEMA, and I'm sure they stepped their game up after that, at least in the New York region, because
Okay.
a lot of houses got rebuilt to actual code rather than being non-compliant.
That makes sense. And then you'd mentioned ASCE 7 kind of may fall short probably, and that you utilize ASCE 41 and the FEMA tech documents. Could you explain just a little bit more about ASCE 24
Yep.
and what that really provides us?
Yeah. So 24 is really like the governing code that a lot of the technical bulletins do a good job of summarizing, and they have a number of them. I think there's 15, or there's a decent amount of them for specific items, and they do good illustrations and, summarize specific key things. But, there's a ton of chapters in ASC 24. Like mentioned, they have some of the loading, probably very similar to the ASC 7 stuff, just regurgitated.
Mhm.
They have equations for, scour depth and things like that, necessary requirements for houses in AE, houses in VE, kind of all that stuff where the flood vents and the breakaway walls come from. But they do dive into like tremendously nuanced things where it sounds crazy, but there's like I would say at least a handful of times I've worked on projects that fall right on a border of flood zones, or the limwa cuts right through, and where the house needs to be, the limwa touches the deck, but it doesn't touch the house. So something, that we had to go back to with ASC 24 because they were like, oh, the house isn't in the limwa. We don't need that. We can have a full enclosed basement, this, that. What we've actually had to do is provide basically a foundation wall for the house, and then just outboard, structurally independent of the foundation, a set of piers, frame your deck on just piers that are not touching the house, and then you kind of walk out, and if the deck gets washed away, it doesn't affect the house. So it doesn't pull the house into the limwa zone, which, is advantageous for having a, solid foundation wall and things like that. So it gets into some very nuanced cases in 24, if you're splitting hairs like that.
Yeah, there seem to be some areas that allow you to make detailed decisions to make a better product or cheaper or like the thing that they want if you do it specific ways.
Yep. And
Um,
things like that, that there was basically we had designed a property with an independent deck, and during an inspection saw that the beams passed over the piers and sat on the foundation wall, and we had to tell them, you got to reframe this deck, like, and they already
yeah.
started some of the finished boards and stuff, and the contractor wasn't happy, and he didn't want, understand or want to hear it, but it was like, listen, man, we did this designation to comply with code. You need to reframe this to meet the designation, and he did, so.
Is there a version that the client can protect the site a little more, raise that elevation up? And what is, if they want to protect the site, how does that look in general? And then can that also be applied to the house? Like this porch in this example, could you raise the site a little bit and so keep the porch out of that, or does that line still hold?
So, um, a big thing goes back to really town conservation, I would say. A lot of these properties that are in flood zones and close to waterways and whatnot are typically kind of considered like wetland boundaries and whatnot, and town conservation has jurisdiction. So another one, on top of the don't do bulkheads, do the revetments, and those are some of the necessary things you would do to protect the perimeter of your property. whether that's bulkheads or a combination of maybe a revetment across the face of your property. And then a lot of times we do like vinyl sheet pile walls coming back and returning to really close off the corners. But in terms of the grading question, the conservation board is very against someone, whether it's in a FEMA zone or like for that purpose, or also when they're just in a wetland zone, just building up their, property because you're going to distribute a ton of, rainwater off to someone else and whatnot. So that's normally not a solution.
So I could just see them building up their houses higher and higher and higher,
Yeah, they just beat the neighbor. That's all that matters.
Exactly. One thing that's interesting and that has come up a few times with, in terms of grading and then the VE walls with the breakaway walls and whatnot. I had mentioned, sometimes a decent amount of the planning happens before sometimes the structural engineer is brought on board, whether that's just the architect or the architect and, a civil engineer starting to plan the site, trying to figure out what's going to happen and whatnot, because you can't bring in that much fill. But even more so with, a lot of times a civil engineer sees a foundation or, a landscape architect sees a foundation and says, oh, we can pile up dirt against that and, start to grade the site like this and get the front yard here. And with, definitely a wood breakaway wall, you can't retain soil on wood. And then a unreinforced CMU wall can't really retain much soil as well. So there has been a couple projects that I've come on, they haven't gone, to construction level drawings, but they were kind of set on this path forward. And then I had to be like, we can't use that wall as a retaining wall. We can't, that needs to be basically an exposed wall. So sometimes we have to work with the civil engineers to maybe adjust grading somewhat. And then sometimes if the other thing too is if you need to retain on kind of one face of the basement, sometimes you can kind of step up the basement from a full height where the grade is low. And then you could step up and make that retaining height and almost go to like a crawl space that, an unreinforced CMU block can resist that level of, 2 to 3 feet of dirt built up against it, but it certainly can't resist, 8, 9, 10 foot basement soil pressure.
Yeah. So thinking coastal protection and something just came to mind. What's the difference of a seawall, a bulkhead? Those two seem pretty close in my mind. What are the differences there, and what materials are being used?
Yeah. So when someone says seawall, I mean, they might be talking about bulkheads, but my mind goes to seawalls are kind of more of like the rock revetment type walls. And then a bulkhead is, the bulkheads are typically, depending on the amount of forces really that are on it, if it's a kind of residential bulkhead that's on maybe like a bay that's, seeing some decent waves and, wakes from, marine boats and things like that. Typically vinyl is kind of a good solution when it's not ocean facing, or in our case, like Long Island Sound has larger wave forces during storms and things like that. Some of the more commercial marinas and whatnot that are seeing bigger boats, larger, maybe partially open to the ocean. They're using steel sheet piles, galvanized steel and things like that to, protect from corrosion. And then with the, the stone revetments or the seawalls, that's where, you're really using, it's called stone armor. So it's a gradation of maybe 1 foot to really like 4 or 5 foot boulders that are the,
Wow.
it's, I always kind of like assimilate it to, everyone kind of knows jetties, they project perpendicular to the beach. These are almost like horizontal jetties, that absorb wave forces in a similar fashion, but yeah.
Have you ever had to rebuild or retrofit a failed seawall? And like by doing that, did you learn anything about how they can fail and how you should design them better?
So in terms of, again, seawall, my brain goes to rocks and whatnot. And
Yeah, I guess that's less likely to fail.
well,
Maybe.
there has been some instances where, there's a couple different ways to protect the shorefront with rocks. A couple of the ways that I've explored, and a big part of that, because of all the environmentalist concerns that I had mentioned on this so far, sometimes the best step for a client is to really go to a environmental consultant. There's a number of them. Some of them do some of this work, or some of them just handle the permitting and the DEC and things like that. But some of them, live and breathe environmental waves, things like that. Like they are marine guys or girls. So they really would be able to guide you based on surrounding properties and whatnot. Oh no, you can get away with a bulkhead here, or we need to do a stone revetment, a breakwaters are way less common. I've done one of them, which is basically you do a revetment slightly into the water. So you got to make sure that no boats are going around or anything like that, but it kind of breaks the waves before it gets to the beach. And then something more recent that we've been exploring with one of the consultants I work with is a cobble berm system, where it's a lot more smaller stones, but you do a pretty thick base. It might be 2 to 3 feet thick, but it's smaller stones, so you're not having to barge in or crane in some of these larger stones. So all that being said, I did investigate one dune that was starting to really erode because someone, and I doubt it was kind of engineered, they just threw a bunch of small rocks down there trying to do essentially a cobble berm type system, but it was nowhere near big enough to resist the wave loading that I was having. So it was really starting to scour the face of this bluff. And we had to come in and design a revetment because it was like, we need to put some big boulders here and then fill back in this sand in this bluff. That's the only way to really like stabilize this. Even more common and very common, I would say, is failed bulkheads. And I think a lot of that has to do with, we've touched on scour a few times. A lot of these bulkheads were built 100 years ago. And maybe the person put in 10-foot 2x12s instead of, a lot of them were built out of pressure treated lumber and things like that, where instead of vinyl sheet piles and things that are really going to last the elements forever. But maybe they put in 10-foot 2x12s and they thought that was fine. But as erosion has continued to happen, the biggest failure is really scouring enough underneath that face, and then the sediment from the back end starting to slide underneath, and then you have basically like a sinkhole on the back side of your bulkhead. So it's less. I mean, I've seen corroded wood and corroded, rotted timber piles and things like that, and that certainly happens. But a lot of the times it's actually losing the sediment down below. So certainly that's how it's kind of helped me. Normally it's kind of a replace because at that point a lot of the steel has been exposed. You see the rust on a lot of, you use a lot of tiebacks with dead men systems, whether that's a helical pile tieback or just like a concrete, cylinder ballast basically that they put back there. The wood's rotting, because that happens over so long. So it's hard to reuse any of that lumber or anything like that. So we normally replace in kind, but we do it with, 10-inch timber piles, some, maybe 4x4, 6x6 whalers spanning between the timber piles, vinyl or steel sheet piles, typically vinyl, the tieback systems. But, learning from some of those failures, sometimes we get pushed back when we call for, maybe 15-foot sheet piles or something like that. And the contractor might be like, we can get away with 10. I don't know why we got to do 15. And it's like, well, the failure happens when we start to scour that. And, as I mentioned earlier, some of the erosion that I've seen over some of the aerial imagery studying some of these sites is only increasing. So, getting a little bit deeper is worth the investment while you're doing the work for sure.
On a lot of these, are they more, I'm trying to figure out how to phrase this, like a typical detail that you then design the depth that it goes into, or most of these walls one-off designs, like, and then, from design or detailing standpoint, are you making the decision based off of cost, longevity? What does that look like with the homeowner? Could you go into that, a little bit more?
Yeah, for sure. I mean, a lot of I would kind of say like a lot of them are typical details, in the 4 to 6 foot retaining, so taking a step back, the wave forces on these, I always envision like it's a wave hitting a sheet pile that has a ton of compacted fill behind it. So it's kind of just hitting a brick wall. So I would say the materials that you use, making sure that they use stainless steel or galvanized steel and things like that for all their fasteners. Uh, using the vinyl sheet piles rather than, sometimes they want to just do the lumber, the vertical lumber, but that's going to rot. So I would say materiality, which is very, industry standard. A lot of people know what you got to do, is kind of the protection against the hydrostatic, but really the corrosive environment rather than the hydrostatic forces. It essentially becomes a retaining wall, that we're retaining a decent amount of soil. So that's where in the 4 to 6 range, that, I could do 10-inch timber piles at typically it's like 6 to 8 feet on center. You go 6 feet when it's 6 feet of retaining. When it's 4 feet retaining, maybe you can get away with 8 feet on center, save them a couple piles. The concrete ballasts, you do a tie back with an 1.5 rod going back to a ballast. So that 4 to 6 range is kind of more of a typical detail, and a lot of contractors know what they're gonna, expect when they see it. It's more kind of putting together all the details and everything for the townships. But there's certainly been, for whatever reason, sometimes someone needs an 8, 9, 11 foot bulkhead, and then that's where it kind of gets a little bit more, and we really got to detail. I like the helical piles in that situation because I could tell them a torque rating, and I know this can hold this much in tension to tie back the system. Looking at the whalers, that's where you might go with a 4x4. 3 4x4 whalers that span horizontally between the timber piles for some of those more traditional bulkheads. But then when you're looking at an 11-foot wall, you got to look at the soil pressure, the triangular soil pressure against your backside of your vinyl sheet pile, which essentially acts as sheathing that spans between the horizontal whalers, which are kind of like your roof rafters. And then you size those for the pressures over the length, say it's 6 feet on center. So that's where you start to really get into nitty gritty, like, calculations and things like that when they're starting to push above 6-foot bulkhead walls.
I have a question that's in the context of ASCE 7 and all code being sort of a code minimum requirement, right? It's not the maximum or what we always have to do. Where do you draw the line between code minimum of a wave wall or any of these structures that we were just talking about and what you might want if it was your house, or what one extra foot might give you if it's a little higher resilience, like against a mean recurrence interval that the design was based on? Yeah, where do you put that?
Your house or grandma's house, let's protect grandma here.
So yeah, with anything with going back to the houses with, close proximity to groundwater, things like that. Like I tend to think things are getting worse in terms of sea level and storm, severity of storms. So that's certainly one place where, you don't, not that you take chances anywhere, but I don't want to, I'd lean on conservative because in 10 years, seawater, groundwater might be a foot higher than it was, and we might be having Hurricane Sandy's every 5 years. So, and that, not to be an alarmist, but it is getting worse with all that stuff.
I have actually, unfortunately, have an interjection question. Is there a thought into that in the code sense of, I have looked at a lot. I lived on the coast, as I said before, but I was thinking, what is ocean rise, ground level rise like projected to be? And it is not projected to be great. So I see the reason to lean a little more conservative in water protection, but is that built into the code at all, or is that just not a thought currently?
I'd say I have a little bit more flexibility with some of these coastal structures because when it comes to the houses, it's, FEMA requirements and it's an AE 8. You need to put your first floor at elevation 10. With some of those things, when it's possible, and I feel like architects have this sense as well, because, we're all living here, we see what's going on and whatnot. I feel like maybe 5 years ago, people were kind of like, oh, just check the box. Let's go with elevation 10. And, we don't want to bring this thing as high off the ground as possible and add a couple more steps to the front thing. I feel like there has been not 100% shift in the industry, but I've seen more and more people be like, hey, let's just get it a little bit higher so that this isn't a worry in, 15 years for these people. So I think that, and I'm not clamoring for this, but like some of the flood insurance studies that I reference for some of the coastal structures are a little bit outdated. Hopefully they're going to get around to doing another one of those flood insurance studies and giving us new still waters that are a bit higher and things like that. The AE and the VE zones, I believe they're staying on top of, because I have seen, or I've been involved with projects that people have said, oh, we looked into this 10 years ago when we were AE 6 and now we're AE 8. So I think it is a fluid thing, and they're trying to keep on top of it. But I think it's one of those things that if you look at the last 20 years, it's been a bit exponential. So it's hard for them right now to stay on top or ahead of it. I think they're trying to, but when I'm designing a hydrostatic basement and I round up a foot on where I expect groundwater, I'll do that. And if we can push the house a foot higher, or, if the still water for 2 transects is kind of a little bit different, maybe I'll lean to the higher one to get a higher, design wave. We're not talking about doubling the design, but it's, getting a little bit more where it ends up being a 6-inch taller revetment that, is at the end of the day, is that going to be the biggest difference? No, but it's just a little bit better,
Yeah, I often think and talk to clients about this minimum code. I always find it so fascinating when they're like, "You're over designing them." It's like, man, we're just hitting the minimum, the bottom that we can. So, I think it's always a productive thing to potential for certain things to increase a little bit, like you're saying. So and maybe this is it. What's one thing you wish every architect or builder understood about designing for water, waves, floods? What are things that are, common misconceptions that you wish they understood?
I think it was kind of like we were just talking about. It's only getting worse, and
Yeah.
When when I tell someone they can only have a 7-foot six basement without dewatering, because dewatering, going through the DEC and everything is months and months, could be 6 to 12 months of just going back and forth with them on dewatering, how much you're pumping out, where are you pumping it to, this, that. So a lot of times we try, and the architects and the clients want to avoid the DEC. So a kind of a general rule is I like the highest groundwater. If it's going to be a finished basement, I recommend the top of your slab, basically the start of your finished basement, is 2 feet separation. Again, going back to that FEMA 2-foot freeboard and everything like that. So that, if we only went a foot and then say that wasn't the highest groundwater because it was a little bit of a dry season or something like that, then groundwater is already 4 inches higher than we anticipated. Now you're only, 8 inches from there. Then you have a storm, and now once you ruin your floor tile or whatever is inside there, then fingers get pointed back at, me, and it's a big cost to redo it. So, sometimes people are like, I don't understand why we need to have a 7.6 basement. Groundwater is low. We've never had a problem with groundwater before. And I'm like, yeah, but things over the last 15 years have gotten worse. Like, it's going to be way worse in 15 years than it was 15 years ago, So, that I would be is the main thing. And, you have those conversations and, normally they start, they accept that you're looking out for their investment, but, it's hard for them to grasp when they've never had, standing water in their basement before.
Okay, so what question have we not asked yet, or questions that you think is really important for our listeners to know?
One thing, I guess, I alluded to it twice, but a nuanced thing between the AE and the VE zone is I talked about first floor elevation, but there's a very specific wording between the two of them. So probably should have addressed this earlier, but here we are. So in an AE zone, you need your finished first floor. So basically the top of your joist plus plywood and whatnot, but most people kind of just do the top of the joist because you don't know if you're going to do a stone floor, wood floor, yada yada. So the top of your joist need to be at the design flood elevation, which is, depending on the municipality, but let's say 2 feet freeboard for now, so that's AE8 is a base flood elevation of 8. Your design flood elevation is 10. In an AE zone, the top of your joist can be at elevation 10. In a VE zone, the bottom of your lowest horizontal member needs to be above the design flood elevation. So it essentially pushes you a foot higher, because say you have 2x12 joists. In an AE zone, the top of them can be at elevation 10. In a VE zone, the bottom of them need to be at the design flood elevation. So it shifts it up an entire member depth.
Sweet. Awesome. Well, Sean, thank you so much again for joining us on the podcast. I know Max and I both learned a ton, something, as we've mentioned a few times, never done before. So thank you so much for your time and sharing everything you know with our audience.
Awesome. I really appreciate you guys having me.
Do you have any references, or I'll throw links into the show notes here for people that want to learn more about this and know less or maybe more than we do, but still need to learn? I want to dive in a little bit. Are there good references that you recommend?
Certainly. Those 2 technical bulletins that I mentioned, I think it was 5 and 9, but then there are a couple also on flood vent opening for AE zones and whatnot. So I'll definitely link up with you after the episode and send you some PDFs, and maybe you can link those in or link the URLs to them. But they dive in, and like I said, it's a little bit easier to read than code because they put in some pictures and whatnot, so it helps.
Yeah, perfect.
All
Awesome.
right.